Alright, today we're going to do two more practice problems for electrostatics. First up, we have two identical charges that are spaced apart by 50 centimeters. And they experience a force that's given to us of 0.25 newtons. The question asks, what is the magnitude of the two charges? Since we're given the force, it'd be a good idea to start off with Coulomb's law. So we're given Fe is equal to 0.25 newtons. And we know that that's equal to K times QA times QB all over the distance squared. Now, we know that A and B have the same charge, so we can do a substitution. And this gives us K times QA squared all over R squared. A little bit of algebraic manipulation later, we have the force times R squared all divided by K is equal to Q squared. So QA is going to be equal to the square root of all of that. The electric force times the distance squared all over Coulomb's constant. Plugging in some numbers, we have 0.25 newtons times 0.50 meters squared. Notice I converted to meters. All over 9 times 10 to the 9 newtons times meters squared per coulomb squared. All of this to the 1/2 power because it's a square root. Now if you're careful with your parentheses and order of operations, you should get a charge of 2.6 times 10 to the -6 coulombs for QA. Now we know that QB was equal to that, so QB is also 2.6 times 10 to the -6 coulombs. This second question is a little more involved. As you can see, we have a test charge, little q, of 3 times 10 to the -9 coulombs, and it is placed in an electric field created by a larger charge, capital Q, which is 25 centimeters away. The test charge then experiences a force of 2.7 times 10 to the -5 newtons from that field. Part A is asking us to find the strength of the electric field. Part B wants us to find the value for the large charge, capital Q. And Part C wants us to figure out what the strength of the electric field is when we increase the distance to 75 centimeters. To solve Part A, let's first remember that the electric force can be written as the charge times the electric field, which means that the electric field in magnitude is going to be equal to the electric force divided by our smaller test charge. Now the force was given to us at 2.7 times 10 to the -5 newtons, and our test charge had a charge of 3.0 times 10 to the -9 coulombs, which gives us an electric field at this point of 9,000 newtons per coulomb. For part B, we need to find big Q. So the electric force we know is Coulomb's constant times little q times big Q over R squared. Rearranging this equation to get Q by itself, we have the electric force times the distance squared, all divided by Coulomb's constant times the small charge. Plugging in some numbers, we have 2.7 times 10 to the -5 newtons times 0.25 meters squared all over 9 times 10 to the 9 newtons times meters squared per coulomb squared times 3.0 times 10 to the -9 coulombs. Notice that newtons cancel with newtons, meters squared cancels meters squared, coulombs cancel only one of the coulombs. We're left with 1 over coulombs, which in the end gives us 6.3 times 10 to the -8 coulombs for the big Q. Now to solve part C, where the distance is now 75 centimeters away. We know that the electric field is equal to Coulomb's constant times the charge that's creating it divided by r squared. So for this problem, we have 9 times 10 to the 9th newtons per meter squared over Coulomb squared times the 6.3 times 10 to the minus 8 coulombs that we just figured out, all divided by 0.75 meters squared. Remember to convert. And this gives us, in the end, approximately 1,000 newtons per coulomb. Now we could have figured this out a separate way. We know that 75 is 3 times further than 25 centimeters, and since it's 1 over r squared, 3 times further away means it's 9 times smaller. So we could have taken our original number and divided by 9 and got the same answer. Now, that might have been the more clever way of going about it, but it is more error prone. So when in doubt, do the calculations, write out your numbers, and use your calculator.